Alright, in this video, what we're going to do is talk about how to derive the acceleration for what is known as an Atwood's machine. So what is an Atwood's machine? Well, it's a very simple machine, and literally it is a simple machine. Remember, in physics, a machine has a different meaning than in everyday life, and so it might not be the type of machine you are necessarily thinking about. But what we have are two masses suspended by a rope that hangs over a pulley, and this is known as an Atwood's machine. Okay, so Atwood's. Now let's call the mass on the left M1 and the mass on the right M2. And we'll say, for the sake of this problem, and according to how I drew it as well, that M1 is greater than M2. Therefore, we look, this entire system is going to move counterclockwise. And we're going to say, for the sake of having a positive and negative direction, that counterclockwise is positive. Now that might not necessarily be intuitive, but I believe it's the easiest way to solve these types of problems, and I'll elaborate on that a bit in a second. So now that we have a positive direction, which is the way the system is going to move, the next step is going to be to write out a picture for each that represents the net forces, also known as a free body diagram. So we'll start with M1 and draw the free body diagram for M1 right here. So we look at M1 and we have its weight downward, and to distinguish its weight from the other mass, we're going to actually call it Fg1 for weight, and the tensile force, or the tension, Ft. No need for a subscript there because the tension everywhere in that rope is exactly the same. Remember, that's a property of rope. Now we come over here to M2 and we do a free body diagram for M2, and it looks pretty much the same. We have the same tension, but we have a different weight, and this weight is going to be called Fg2. Now that we have the free body diagrams, we can write a net force equation for each of our two masses. So what is our net force equation going to be? Well, the net force, according to Newton's second law, is always equal to ma. So let's start over here with m1. And what is the net force equation for m1? Well, it's going to say F net, and F net must be equal to the sum of all of the forces acting on this particular mass. So we have tension and weight. Well, earlier I established that counterclockwise is positive. So what exactly does that mean? Well, what it means is if we followed this arrow that I drew, so on the right-hand side, it would go upward and then around the pulley, and then on this side it would point down. If a force is in the same direction as the arrow, it's going to be positive. So on this side, weight is positive, but tension is in the opposite direction, so it's negative. Whereas on this side, tension points with the arrowhead, and that's positive, and weight will be negative. So our net force equation then for M1 is going to be our positive force, Fg1, minus tension. Well, Newton's second law says that F net must be equal to ma, and which mass are we talking about? M1. So we must distinguish this mass from M2. What is Fg1? Well, that's the weight. How do we find weight? Just mg minus tension. The next step is going to be to solve for tension, and the reason that we do this is because we're also going to get an equation for M2, which is going to have tension in it. Because tension is the same for both this side and this side, what we can do is use simultaneous equations and solve one equation for tension, plug that into our other equation, and get rid of tension completely as a variable. So let's go ahead and solve for tension. It will be equal to m1g minus m1a. Now I'm going to go and solve for M2, find its net force equation. So F net is equal, well, on this side, up is positive, so we have tension minus weight, Fg2. Well, F net for this one is just M2A, and that's going to be equal to tension, but tension, we found, is this. Because it's the same on both sides, we can plug it in there, and we get M1G minus M1A minus the weight of this guy, which is M2G. So now we have an equation that only has mass, acceleration, and gravity in there, and my ultimate goal is to determine the acceleration for the entire system. So I'm going to do a little bit of algebra, collect like terms. So I'm going to get M1A, and add this to both sides, plus M2A is equal to M1G minus M2G. I'd like to factor out A and G just to simplify things a bit. So I get A times M1 plus M2 is equal to G times the quantity M1 minus M2. So now, if I want to solve for acceleration, all I have to do is divide by this quantity here, M1 plus M2, and that leaves me with the final equation for the acceleration in an Atwood's machine, and that's going to be equal to the quantity G times M1 minus M2 divided by the sum of masses M1 plus M2. So there is the acceleration of our system. And once you knew the acceleration, so if I gave you the masses, and we're on Earth, this is just going to be 9.8, then you can back substitute, perhaps into this equation, and determine what the tension in that rope is. So this is an Atwood's machine, which is a simple form of a coupled forces problem.